Okay, we'll continue here with the ancient Greeks, and it was around the turn of BC to AD, I guess around 200 BC with Aristotle, that astronomy really started to develop separate from astrology. When we get to the summation page, we'll pull all those ideas together, but suffices to say that with the ancient Greeks, when the world culture and learning center was in Greece, that's when we had sort of a revolution in thought and how to understand the universe. It was a walking away from, so to speak, a walking away from religious ideas, gods and goddesses, to more rational thought, logic-based, and based on observation, and even supported with math in some respects. So we'll take a look at what we have here. Because much of the recorded history of the ancient civilizations prior to ancient Greece has been destroyed, a lot of textbooks will go ahead and just say that the history of astronomy really starts in Greece. Well, we talked about a whole slew of evidence that kind of disputes that no, astronomy really began with the very earliest of humans, probably just making simple observations. But formal astronomy with observations where people were sitting down or setting out at night to make specific observations of the nighttime sky basically began in Greece. That's where the world culture and learning center was at the time, kind of centered around the Mediterranean area, Great Library Alexandria in Egypt, and of course Greece. So everybody who wanted to learn or make something of themselves academically would flock to Greece from all over the world, really. The Greeks really built on a lot of extensive written records, previous cultures, which gave them some success in being. This is one of the big ideas here, the split. The Greeks approached astronomy not with the mindset of worship or divination, but to try and just understand. They said, hey, maybe the reason we don't know how things work is not because it's not understandable, but just because we don't understand it right now. So that's that quote there, the mysteries of the universe are mysteries because they are unknown, not because they're unknowable. So the Greeks early on, now this is way back 600 BC, so this is very early on, Thales says this, and it's a concept that a lot of Greeks bought into and said, I think we can understand this universe. If we just put our minds to it, we'll eventually figure it out. And so scientific method and things like that are coming out of this time frame. Pythagoras went on to claim that the rules of the universe must be mathematical. During this time, the big idea was a geocentric model, although heliocentrism was proposed too by Aristarchus. Geocentric is what most people bought into, just because observations really are evidence. They evidence that idea. You look up at the nighttime sky and things appear to go around us, and we appear to be in the center of everything. All right. So Occam's razor before William of Occam. Occam's razor is a scientific principle that states all things being equal, the simplest explanation tends to be the right one. And according to the Greeks, when they looked up at the sky, they would notice things going around Earth and going around in their sky. And what's a more simple explanation? That the Earth turns and it's at the center of everything, or that there's a complicated universe with lots of motion, and we're actually orbiting the sun and the rest of the planet. It doesn't look like that. So to them, that was an illogical and very complicated conclusion to reach from relatively simple observations. So that's the principle of Occam's razor, and it's a very old principle. Okay, and if you go into any kind of science field, you'll encounter Occam's razor again. So the ancient Greeks, here's a model of the celestial sphere, which is a geocentric model of the universe. We have on the outside a solid crystalline sphere, the Earth at the center, the moon going around the Earth, the planet, and the sun is kind of third out, Mars beyond the sun. And that's how they thought the universe was structured. They thought that Earth must be God's creation, so it's at the center, it's very special, and everything goes around the Earth. And it certainly looks like that, but we know it's not the case. So the celestial sphere is a big concept with the ancient Greeks. The anything that didn't move around, like the planets, was thought to be in the outermost sphere, and then the known wanderers were the other planets. So we begin with Aristotle. He thought the universe was two parts, corrupt, unchangeable, very geocentric due to lack of parallax, which is a shift of stars. If you look at, you can do this experiment. Parallax can be seen all the time. If you want to right now, you might look a little silly sitting at your computer, but look off somewhere and have one finger out at arm's length. So hold up your pointer finger at arm's length, and you should do this just to prove to yourself what parallax is. If you're looking at your finger, you can see one finger, but if you look beyond your finger to the wall, your finger splits into two. Now close one eye, keep your finger still, and then switch eyes. Don't move your finger, but just switch eyes back and forth, and you'll notice against the background of whatever you're looking at, your finger appears at a different position as you switch eyes, okay? And that's parallax. That's the shift of the apparent location of your finger. Not that your finger's actually moved, it's what appears in the background, because there's a little bit of space between the two pupils of your eyes. There's a few inches there. So you're looking at your finger from slightly two different areas or positions. And Aristotle knew that this should happen. Hold on, I got an announcement here. Okay. Oh, we got to check an email. Sorry about that. I got an announcement happening here at school, so I just had to listen to that. But anyway, parallax, he didn't notice parallax. Not because it didn't happen. It was happening, but he didn't have the correct instruments to view it. The shifts of stars are so small as our Earth goes around the sun. So we basically see these positions of stars against the background from two different locations that we need a telescope to see them. He actually proved the Earth was round pretty cleverly using the ships as they sailed over the horizon. They appeared to sink, but of course they weren't sinking. They were just going over the curvature of the Earth, and then they would later come back. So he deduced that, hey, they must be going over the curvature of the Earth. If the Earth were flat and they were sinking, then they obviously wouldn't come back, right? They would be sunk. And then he looked at a lunar eclipse and saw that the shadow of the Earth on the moon is rounded. And a rounded object casts a round shadow. You wouldn't expect to hold a basketball up to a light and look on the wall and see the shape of a triangle. That would be really freaky and, probably mess with your head a little bit. He just used simple logic there. He was the authority on learning. Everybody followed him. Then we have this guy Aristarchus, around the same time. He was the one that first suggested a heliocentric model, which is sun-centered. Used simple geometry to try to calculate the distance Earth-Moon and got a rough estimate, but it wasn't very accurate. Calculated the relative sizes, again, lacked accuracy. But he did conclude that the sun was a lot larger than the moon, and that was correct, and that's pretty impressive for back then with not a lot of instruments. Because Aristotle was such a popular guy, and as far as the academic world, he would be like the Einstein of that age. Everybody thought he was just the greatest. Aristarchus didn't get a whole lot of attention, but he had a lot of right ideas. This guy Eratosthenes, tough word to say, Eratosthenes. It's STH. That's the hard syllable right there. Eratosthenes. He calculated the circumference of the Earth very accurately using the noonday sun rays, a well, and the angle of some shadows. And I think I have a picture coming up. If not, then you can look that up on your own. So here it is. He got a really good estimate for the size of the Earth. And what he did was he had a well in Syene, or the well was in... Yeah, it was a well in Syene, and then there was this town, Alexandria, a little bit away, and there was some distance. And what he did on a day that he knew the sun's rays would go to the bottom of the well, which we can extend a line to the center of the Earth, he was in Alexandria measuring the shadow rays on a stick. And because the Earth is curved a little bit, there was a little bit of a shadow on the stick, and he associated that angle on the ground with this distance. And if he knew that the Earth was round, 360 degrees, and this angle was 7 degrees, he multiplied or divided 360 by 7 and got this distance of about 52 stadia, or maybe 52 miles. But basically, he figured out this distance and then multiply that by 52. Oh yeah, that's how many times 7 goes into 360, and you get the circumference of the Earth. So pretty cool on what he did there. Hipparchus was the greatest known observational astronomer. That's what OA stands for. You can see he's kind of using a sight instrument. They have telescopes, but this is not a telescope, but it's a sight. Kind of like you have on a small pellet gun or something like that. You just have a sight, a little guiding peg that you can line stuff up with. Nothing magnifies or anything like that. But he made a whole star map just using instruments like this, star catalog. 850 stars divided into brightness categories. We still use the Hipparchus magnitude system today. Measured the length of the year, predicted eclipses, discovered precession. Again, you kind of get the theme that we're doing a lot of observations here, specific observations, detached from the whole religious or spiritual idea. He also discovered precession, which we'll talk about in another unit. Precession is the wobble of the Earth's axis. Calculated accurate distances to the moon, and also invented trigonometry. So this guy has a very impressive resume, you know, as far as the other astronomers. Now, Claudius Ptolemy, and I know there's a P there, but you don't pronounce the P, it's silent. Claudius Ptolemy was the most famous of the ancient Greek astronomers, and his models, the Ptolemaic system, lasted all the way up into Copernicus, which we'll pick up with the next lecture, with the development of classical modern astronomy. Claudius Ptolemy's geocentric system was accepted by the church and taught as fact. He wrote this big long book called the Almagest, which is translated to Great Work. He was Egyptian and he lived in Alexandria. He was the head of the library there for a while. If you don't know what library I'm talking about, the library in Alexandria, you should go do some research and look up what that is. It's one of the most famous libraries of all time. He created a mathematically based geocentric model, and that was powerful enough, but what his model could do that a lot of others couldn't was make predictions of the positions of planets, and that's why everybody was like, okay, well, this has to be right. And still, it was geocentric, but his model worked. He explained retrograde motion with these epicycles and stuff we'll look at in a second in a picture. Lasted for 13 centuries, or about 1,300 years, and he was even adopted by the Catholic Church and taught as fact. So system of wheels within wheels to describe these motions of planets, epicycles, and deferents. And this is what his model looked like. So the Earth was at the center, the moon went around the Earth, then Mercury, Venus, and the sun were on this straight line. Kind of, they would go around together, but Mercury and Venus were on these smaller circles called epicycles, okay? And the distance was called the deferent here, and so Mars, Jupiter, and Saturn also on epicycles, and then we hit the celestial sphere where the stars were on the very outer edge. And everybody thought this is how the universe was for over 1,000 years, if you can imagine. 1,000 years, people accepted this as fact. This was how the universe was. Earth is at the center, it makes sense, but eventually after 1,000 years, his predictions using this system, they started to not match up with observations, so we had to return and rework it, and they ended up just kind of dropping it, and then Copernicus came along with his theory. So errors over time, yeah. So the summary of the Golden Age, which is all that we talked about. When we talk about Greeks, we're talking about Golden Age. Universe was considered to be understandable, which was a deviation from supernatural. Observations, made with simple tools and functions of sights. Natural explanations for observed phenomena. The scientific method comes to play, to fruition here, which is observe, hypothesize, predict, test, observe, return to, or conclude. Math-based understandings, including models that were mathematically based that could make predictions, such as the Ptolemaic universe, and cosmological models based on observations, not just supernatural explanations. And we'll pick it up next with Nicholas Copernicus and the start of classical modern astronomy.